Throughout this chapter, we've been talking about infinite series and determining whether they converge or not, but we've never talked about why we care. What is the purpose of an infinite series? One such purpose is that series can be used to approximate functions. If we use a finite series of a certain form, it can give us a very accurate approximation of what the actual function does, but it can do it using a polynomial rather than a more complicated function. What I have here for an example is sine of x. Now, sine of x is not a complicated function, certainly, and yet it certainly is not what a polynomial does either. So you might ask, of course, well, how can a polynomial possibly approximate what sine of x does? Polynomials have end behavior that go towards infinity and negative infinity, depending on the degree and lead coefficient. But sine of x, no matter how far out to the left or right you go, always stays between -1 and 1. So how can a polynomial possibly approximate it? Well, first of all, it can approximate it, but typically only on a limited interval, a relatively small interval of input values. But that being said, the thought behind it is that in order to have a polynomial approximate a non-polynomial function, it needs to match certain characteristics. Now, in a previous unit, we've already seen some example of this, whether we realized it at the time or not, and that was in numerical integration. In numerical integration, we used 3 different shapes to approximate the value of a definite integral. We used rectangles, whether it was left endpoint, right endpoint, or midpoint. We used rectangles. We used trapezoids. And then we used parabolas. We called that Simpson's rule. And the idea is this, that let's say, for example, we have sine of x on 0 to pi, and let's say we split it into 2 subintervals. The idea of the midpoint rule with rectangles, or the trapezoid rule with trapezoids, or Simpson's rule with parabola, is how we are approximating the top of the interval. In using a rectangle, and again, we'll use the midpoint rule here. In using a rectangle, the idea is to find the y value at the middle of the interval and use that to define the top of the region. In this way, we're using a horizontal line to approximate a curved function. This is incredibly inaccurate. The only thing that this horizontal line and this curved function have in common is they share one single y value at one single point. And that's all they have in common. Then we move to the trapezoid rule. And the trapezoid rule said that we were going to approximate by using a linear function, a diagonal line. And the idea is that this diagonal line gives a better approximation for what the function is doing, if for no other reason than it also represents that the function is increasing on this interval. The horizontal line for the midpoint rule, for the rectangles, is incapable of representing whether a function is increasing or decreasing. That is to say, if we were to go to the second subinterval, we would find the exact same thing. And yet, the function is doing 2 different things on each subinterval. On the left side, it is increasing. On the right side, it is decreasing. And yet, we have the exact same horizontal line representing both sections. On the other hand, by using a linear function, we can now see the difference in how on the left side, where the sine of x curve is increasing, the linear function also has a positive slope. And on the right side, where sine of x is decreasing, the linear function again has a negative slope to represent that. Now, we're not talking about the area underneath the curve here. So I know that when we talked about the midpoint rule and the trapezoid rule, we actually found that the trapezoid rule wasn't that much more accurate than the midpoint rule. In fact, sometimes it was a little less accurate. So it wasn't, in this case, it's not about the accuracy of the area under the curve. It's about the fact that we are matching up more characteristics of the curve with a higher degree polynomial approximation. So that is to say that the red line, the horizontal line, matches a single characteristic on that interval, one single y value. The blue diagonal line actually has three characteristics because it matches up two y values, one at the far left of the interval and one at the far right. And it also matches the fact that the function is increasing. So it is including more information that represents what the actual function is doing. We then got into Simpson's rule. And Simpson's rule, going along this same vein, Simpson's rule is now going to match 3 points. And not only is it going to match the increasing and the decreasing, it actually takes a step further and it matches the curvature as well. Neither the red horizontal lines nor the blue diagonal lines represented any kind of concavity because they aren't high enough degree to have curvature. But Simpson's rule uses a parabola, and that parabola allows us to also approximate the curvature, because on this interval from 0 to pi, sine of x is not just increasing and then decreasing, it is also concave down along the entire interval. The parabola is capable of representing not just the 3 points, but also the increasing and decreasing, and also the concavity of the function. Now, if you can imagine, if we were able to go to a higher degree polynomial, now what it is a third derivative or matches, what it is a third derivative tells us about a function is considerably less clear, or a fourth derivative or fifth derivative. But the point is that if we go to higher and higher powers for a polynomial, we have more derivatives available to us to match the more derivatives that the sine function has. And we know from differentiation that sine can be differentiated infinitely many times. And it cycles through sine to cosine to negative cosine, and finally back to sine. And that can continue forever. Polynomials have a finite number of derivatives in the sense that eventually their derivatives will cycle down to a 0, at which point it ceases to become productive to continue differentiating. But in the interim, all of the derivatives that do exist for the polynomial can mimic what the derivatives of the sine function is doing, or any other function we choose to use. This concept is what's going to give us the idea of what is called a Taylor polynomial. The concept of a Taylor polynomial is we want to use a polynomial function to approximate the behavior of a non-polynomial function by matching as many characteristics of that function as we can. We want to match first the output value itself. That's what the red horizontal line is doing. It is only matching the output value of the original function at one single point. We expanded that to the blue diagonal line by saying, well, now we can represent whether it is increasing or decreasing, which is measured by the first derivative. We then went to the green parabola, which has the capacity to measure match not just output values and not just increasing and decreasing, but also to match concavity. Now, that's where we're going to run out of names for stuff, but the idea is that the output value is matching is matching f of a, the output value of the function, but in order to match increasing and decreasing, we need to be matching the first derivative. In order to match curvature, we need to match the second derivative. So at this point, we run out of names that we're familiar with for what these things measure, but the idea is that we want a polynomial to match n orders of derivative of the function. We can take this as far as we wish. We can only match the output value. We can match the output value and the first derivative. We can match the output value, first derivative, and second derivative. We can go as far as we choose to with this. The further we go, the better our approximation of the function will be. And the wider the interval, it will be reasonable to use that approximation on. Now, unfortunately, it's not quite as simple as we might like in terms of just matching the derivatives. There is a bit more to it than that. I am going to start with the definition of what a Taylor polynomial is. We're going to start with with a generic function. And specifically, we're going to say that it is differentiable n times. So we can differentiate it at least once, twice, 3 times, to whatever level we choose to be. Now, it doesn't necessarily have to be differentiable everywhere. We're just going to be interested in a certain specific point. We're going to have a polynomial of degree n, p sub n. And that polynomial function, of course, is going to have an input. This polynomial is going to match the output value of the original function at the target point x equals c. It is then going to also match the first derivative. And then that's going to be multiplied by x minus c. We will explain why that minus c is there as we prove this. Then we're going to have the second derivative matched at x equals c. But we're going to introduce a new idea here, that this is going to have a denominator that the previous two did not have. That is to say, they actually do have one, but we tend not to write it because their denominators are equal to 1. If I may, this could be thought of as having a denominator of 0 factorial, whereas this could have a denominator of 1 factorial, where 1 factorial is obviously just 1, and 0 factorial, with an interesting non-intuitive result, 0 factorial is actually defined as being equal to 1 as well. So those two terms do have a factorial in the denominator. We just don't see it because it simplifies in such a way that it's not necessary for it to be written. So we now have the second order derivative over 2 factorial times x minus c squared. Then we would have the third derivative at c over 3 factorial times x minus c cubed. And this pattern would continue to the nth order derivative at c over n factorial times x minus c to the n. P sub n of x, then, is the nth degree Taylor polynomial for f of x centered at x equals c. Now, where did this come from? Why are there factorials in the denominators of these? Now, why is there an x minus c? The x minus c should be easy enough to explain because the minus c is nothing more than a horizontal shift. There's actually something known as a Maclaurin polynomial. A Maclaurin polynomial is exactly the same, but it is centered at 0. Therefore, a Maclaurin polynomial is of the form f of 0 plus f prime of 0 times x minus 0, or just x, plus f double prime of 0 over 2 factorial times x minus 0, or just x, squared. And then the third derivative at 0 over 3 factorial times x minus 0, or just x, cubed. Going as far as the Taylor polynomial did. In this way, it looks more like what we would expect a polynomial to look like, x to a power with a coefficient, where the coefficient specifically has to be the nth derivative at the centering point over n factorial. The minus c that we see in the Taylor polynomial is nothing more than a horizontal shift. It takes this more basic form that we see in the Maclaurin polynomial and allows it to be shifted horizontally to a new position so that we can center at a different x value. That is the function of the minus c. The powers, of course, give us the different powers of x that we expect to see in a polynomial. And the nth order derivatives and the factorials underneath them give us the coefficient of each term. So the real question is here, why on earth do we have to have the nth order derivatives over n factorial in the way that we do? Well, let's start with the assumption that this is true. Let's start with the idea that if we're going to have an nth degree Taylor polynomial, that it has to have a coefficient, a constant term, and then a coefficient times x to the first, allowing for a horizontal shift, plus some coefficient times x squared, x minus c squared for the horizontal shift, plus some coefficient times x minus c cubed, etc., so that each one of these things has a coefficient, and it's our job to figure out what that coefficient should be. The idea of this, of course, is that we are also supposed to match derivatives. So if we do that, the derivative of this, p sub n prime of x, well, the derivative of the constant a sub 0 is 0. The second term is linear. Now, it is technically a composition. It has an x minus c inside the parentheses, but since this is a linear inside function whose derivative is 1, its inside function has no effect on the derivative. So what we have here essentially is a sub 1 times x to the first. The derivative of a linear term is the coefficient of the linear term. The exponent would drop from x minus c to the first to x minus c to the 0, which would cause it to simply drop off. Then we would have the coefficient a sub 2, and we would have the x minus c squared. The derivative of something squared is 2 times that thing to the first power. And again, since the inside function is linear with a derivative of 1, we do not need to consider the derivative of the inside function here. Likewise, we would then have 3 times a sub 3 times x minus c squared, all the way up to the end where we would have n times a sub n x minus c to the n minus 1. So in this way, we have matched, we are differentiating this polynomial. But the idea, of course, is that all of the derivatives are supposed to match. So we now go to p double prime. Now, in the first time we did this, I wrote the 0 here because I wanted to emphasize that the derivative of the constant term turns into a 0. I think we can drop that at this point. So we know the derivative of that 0, since it isn't anything to begin with, its derivative is 0. We have a sub 1, its derivative is also 0 since that's a constant. So we can move right down to 2a sub 2 times x minus c to the first. Now this is a linear term because its exponent is 1. The derivative of a linear term is simply its coefficient. We then move to the next term, where the derivative, the coefficient, carries through, and then we have the 2 come down in front, and the power drops by 1. Now, I could directly multiply the 2 times the 3 and get 6, but I actually want to keep the 2 and the 3 separate there so that we can see them both. Now, I didn't write a higher power term to begin with, but by using a little bit of logic, we can say that let's go to what in the original function would have been the fourth power term, a sub 4 x minus c to the fourth. In the first derivative, that would have become 4a sub 4 x minus c cubed, which means when we get to the second derivative, it should now be the 4a sub 4 that's already there, times the 3 that comes down in front, times x minus c with a power that has now dropped to 2. And if we continue this, we're going to have n a sub n times the n minus 1 that comes down in front, and then the power on this drops again to n minus 2. If we take this one step further, which I think should be enough to see the pattern, we realize that 2a sub 2 is now a constant, so its derivative is 0. What we then have is the linear term, whose derivative is simply going to be its constant. Now, I'm going to add one other thing in here that we don't typically write, but I think would be helpful to see here. That when we have a linear term, its power is 1. So when we differentiate, the power of 1 comes down in front, and then the power drops to 0. When we differentiate here, the power dropped to 1. The 1 came down in front, and then the power dropped to 0. Well, that's going to happen again in this third bit. The 1 is going to come down in front, where we have the 2 times 3 times a sub 3. And then the power on the x minus c drops to 0. For the next term, we're going to have the 3 times 4 times a sub 4. The power of 2 comes down in front, and the power drops to a 1. What we can hopefully see now is that as we do this, because the very nature of polynomials is that we have integer powers, and each step of differentiation causes that power to drop by 1 and brings the power down in front, we're literally going to have coefficients that end up with the original power of the term times 1 less than it, times 1 less than it, times 1 less than it, counting down. And what ends up happening here is that by the time we get to the nth derivative, we're going to have exactly what is necessary for a factorial. N times n minus 1 times n minus 2 times n minus 3, counting all the way down to 1. Now, we need to match this with the function. And it specifically has to match it at the target value. So since the polynomial function is approximating the original function, let x equals c, we're going to substitute c for both of them. The idea is that at the target value, we are supposed to be matching what the function does. Now, what we've got here is that p sub n of c is going to be equal to a sub 0 plus a sub 1 times c minus c plus a sub 2 times c minus c squared, etc., plus a sub n times c minus c to the n. And the idea, of course, is that every one of these c minus c's is equal to 0, which means every one of these terms drops out. And what we have is that p sub n of c is equal to a sub 0. But we also know that p sub n of c is equal to f of c. Therefore, a sub 0 has to be equal to f of c. Taking it to the next step, we have p sub n prime of c is equal to f prime of c. Again, the whole idea is that we are supposed to be matching the different characteristics of the original function at the target point. Well, we know that p sub n prime, we have that up here. P sub n prime is equal to a sub 1 plus 2a sub 2 times x minus c, but we are substituting c in for x, plus 3a sub 3 times c minus c squared, plus 4a sub 4 times c minus c cubed, plus plus n a sub n times c minus c to the n minus 1. Where again, because c minus c is equal to 0, that's going to cause every one of these terms to drop out. And what we're left with at the end is that p prime of n, or p sub n prime of c is equal to a sub 1. And we know that that already is equal to f prime of c. Now, so far, it seems like, hey, isn't just a sub n equal to the nth derivative at c? And so far, we've been lucky because, again, these things don't have a factorial denominator because the powers we've been dealing with are small enough that they haven't actually contributed to it. So we're going to take one more step further here and talk about p sub n double prime of c, which again is supposed to match f double prime of c. We are supposed to be matching the characteristics of the original function at the target value. So what this gives us is p sub n double prime of c is equal to 2, well, let's do the full thing here, 1 times 2 times a sub 2 plus 2 times 3 times a sub 3 times c minus c to the first plus 3 times 4 times a sub 4 times c minus c squared, all the way up to n minus 1 times n, a sub n, c minus c to the n minus 2. And once again, the c minus c is going to cause each of these terms to drop out. And what we have now is that p double prime, or p sub n double prime of c is equal to 1 times 2 a sub 2, and that is equal to f double prime of c. Now the purpose of this is to identify what are the coefficients of each term in the polynomial. So far this has been very direct. The coefficient a sub 0 is equal to f of c. The coefficient a sub 1 is equal to f prime of c. In this case, in order to get a sub 2, we're going to need to divide both sides by 1 times 2, also known as 2 factorial. And perhaps you can already start to see where we're going to get the factorials in the future terms. We will do one more to help establish the pattern. Let's go to the third derivative, p sub n triple prime, which has got to be equal to f triple prime. We would now have 1 times 2 times 3 a sub 3, and then 2 times 3 times 4 times a sub 4 times c minus c to the first. Now I could continue to write out other things here, but I think we've gotten the idea that when we do this, when we substitute x equals c, that all of these other terms have a c minus c factor in them. So regardless of their coefficients or the powers on them, each of them is going to drop out because the c minus c creates a factor of 0. So at each step of this, we get that p, in this case, p triple prime is equal to simply the constant term that is left there. And as before, in order to isolate the a sub 3 in this case, we need to divide both sides by its coefficients, which are its original power times 1 less than that times 1 less than that, and so forth, also known as its original power factorial. And that is how we arrive at the factorial denominator. Now, at some point, you must be wondering, how does this figure into series? We haven't yet seen a single bit of summation here. Well, p sub n of c, p sub n of x is equal to f of c plus f prime of c times x minus c to the first plus f double prime of c over 2 factorial times x minus c squared plus f triple prime of c over 3 factorial times x minus c cubed to the nth derivative at c over n factorial times x minus c to the n. This is a finite sum, not an infinite sum, but a finite sum of terms that follow a specific pattern. The pattern that it follows can be written with summation. A partial sum, not an infinite sum here, where starting at I equals 0, where each term has a coefficient a sub 0, or a sub 1, a sub 2, a sub 3, and x minus c to a power, x minus c to the 0, which does not get written, x minus c to the first, x minus c to the second, and so forth, where each a sub I, as we showed previously, each a sub I has a very particular relationship. A sub I is equal to the ith order derivative at c over I factorial times x minus c to the I. This is how this connects to summation. Now, we don't necessarily need to use the summation to write it because it is a finite sum. You might ask again, how does this connect to infinite series? The idea is that if we allowed n to get larger and larger and larger, we would get a better and better approximation. This is a topic for another lesson, but it should be noted that as n approaches infinity, p sub n of x approaches the actual function for all x. Instead of just being centered at one particular point, and as we vary from that point, the approximation becomes less and less accurate, we broaden the interval on which that approximation is valid. And if we could go up to 100 terms, a 100-degree polynomial, or a 1,000-degree polynomial, we would get such an incredibly large interval of incredibly accurate approximations that eventually the difference between them would be negligible. That is a topic for another lesson, but what we are going to talk about is how do we define the Taylor polynomials and show how the approximations are very accurate as long as we stay relatively close by. Let's start with a straightforward example, one that will be very easy to work with. We're going to find the third degree Taylor polynomial for e to the x centered at x equals 0. Now, just to pop this out there again, we know that p sub n of x is equal to the sum from 0 to n of the nth order derivative at c over n factorial times x minus c to the I. Excuse me, those should be i's, not n's. The ith order derivative over I factorial times x minus c to the I. Where in this case, since c is equal to 0, what we really have is the sum from I equals 0 to n of the ith order derivative at 0 over I factorial times x minus 0, or just x by itself, to the I. So we picked a nice centering value for a first problem to make it easy. What we need for each of these, and x to the I is easy to do, I factorial is easy to do. What we really need is the ith order derivative of e to the x. So we need the function itself. That's the 0th order derivative, if you will. We need the first order derivative, which, well, since it's e to the x, its derivative is also e to the x. We're going to need the second order derivative, which is, well, also e to the x. And because we are going up to a degree 3 polynomial, we're going to need the third order derivative, which is also e to the x. Nice and simple. A nice, simple place to start. We also need the value of each of these at the center, at the target value, x equals 0. And fortunately, since all of them are exactly the same function, they also all have exactly the same value for the ith derivative at 0. So, what we have then is that p sub 3 of x is going to be equal to the 0th order derivative over 0 factorial times x to the 0 plus the first order derivative at 0 over 1 factorial times x to the first plus the second order derivative at 0 over 2 factorial times x to the second, plus the third order derivative at 0 over 3 factorial times x cubed. Please note again that 0 factorial is defined as being equal to 1. Again, that is a topic for another day. So we have 1 over 1 times x to the 0, which is 1. And then we have 1 over 1 factorial times x to the first. 1 over 2 factorial, which is 2, times x squared. And then 1 over 3 factorial, which is equal to 6, times x cubed. To simplify this down, 1 over 1 is equal to 1. And x to the 0 is equal to 1, so that entire first term is just equal to 1. 1 over 1 in the next term is also equal to 1, so we can simply write x. And then 1/2 x squared and 1/6 x cubed. And this is the third degree Taylor polynomial for e to the x centered at 0. Now, what is the purpose? So we found this, big deal. But why? Well, again, let's remember that this is an incredibly simple function that we're working with, and it is only a very first example, so things worked out very simplistically. It also makes the purpose of doing this seem trivial, because the purpose is to say, great, now this function can give us an approximation for what e to the x is doing. So let's take a look at that. Let's build a table of values. where we're going to compare the actual value of e to the x with the Taylor polynomial value, the third degree Taylor polynomial value at that same x value. We're going to start at the centering value of x equals 0. We have e to the 0 is, of course, equal to 1. And if we look at the Taylor polynomial, it's just a polynomial. Polynomials are very easy to evaluate, especially at x equals 0, because it makes all of the terms drop out except for the constant term. Perfect. So what we can see is that at x equals 0, at the centering value, the Taylor polynomial is providing the exact value of the original function, and that is what it is supposed to do. The question is, though, what happens if we start to vary a little bit? What happens if we go out to, say, 0.1? Now, we would need to pull out a calculator for this to do e to the 0.1, because honestly, we have no way of doing e to the 0.1 without a calculator. Interestingly enough, you might say, well, wouldn't I need a calculator to do p sub 3 of 0.1? And the answer is no, actually, because e to the 0.1 is difficult. It's an exponentiation with an irrational number for a base. Not only that, the exponent itself is kind of awful to work with. Even if it was a nice base, even if it was 2 to the 0.1, how would we even figure that out? But for the polynomial, if all we had was pencil and paper, could we actually do 0.1 to each of those powers? And the answer is absolutely we could. It might take a little bit of time to do it by hand. We might not like doing it by hand. But imagine yourself a couple hundred years ago before calculators were around. Believe it or not, this is how they figured out what many of these things did. A Taylor polynomial allowed us to come up with a very reasonable approximation for the value of e to the 0.1 by using a polynomial, which you could do by hand if needed. And if you didn't have a calculator, well, how else would you do it? So we're going to start with p sub 3 of 0.1. Now, I'm not going to actually do all the arithmetic by hand here. We're going to hand wave that. But if we did do all the arithmetic by hand, we would get 1.105,166 repeating. Not that big of a deal. Somewhat easy to see where that comes from, by the way, because and I will just quickly jot this part down, we would have 1 plus 0.1, and then we would have 1/2 times 0.1 squared, which is 1/2 times 0.01, and half of that would be 0.005. So what we can see here is, here's the 1 in the ones place, here's the 1 in the tenths place, and then a 0 and a 5 to get us to the hundredths and the thousandths place. And then we would have 1/6 times 0.1 cubed. 0.1 cubed is easy enough because it is 0.001. 1/6 of that, well, hopefully we can recognize 1/6 as a decimal. It's 0.16 repeating. And all multiplying by 0.001 is going to do is move the decimal point 3 spaces. So here we have our ones place, our tenths place, our hundredths and thousandths place, and then for our 4th decimal place and onward, we have those. This is not all that hard to come up with by hand. E to the 0.1, however, we would have no choice but to go to a calculator. And interestingly enough, the value of e to the 0.1 from a calculator is 1.10517, etc. That's very close. That has the same number in the ones place, the same number in the tenths place, the same in the hundredths, the same in the thousandths, the same in the 10,000ths, and only in the 100,000ths place do we first see a difference, and it's not even that big of a difference. That's an incredibly accurate representation. It is within 100,000th of the actual value of e to the 0.1. And we're going to speed this up a little bit. We're going to go a little bit further away from our centering value. And again, while 0.02 is maybe not quite as friendly as 0.01, it is something we could do by hand in the polynomial. Hand waving that a little bit, we would get from this 1.2213, whereas e to the 0.2 would be 1.2214. In this case, we see our difference not in the hundred thousandths place, but in the 10,000ths place. So we see that difference in their values a little bit sooner because the polynomial is a little bit less accurate as we get further away from our centering value. Let's take a larger leap and go a full integer value away. E to the first, which is a value that hopefully we should be somewhat familiar with. E itself is 2.71828, etc. The polynomial here is actually incredibly easy to evaluate because if x is 1, then all the powers of it are just 1, and we end up just adding the coefficients together. And what we end up with is 2.666 repeating. We can see here now the difference in their values is evident as early as the 10ths place. These two numbers are still relatively close, but with a noticeably larger difference than we had when we were only at 0.1. It does work just as well going the other way, where if we would have had trouble doing e to the 0.1, doing e to the negative 0.1 would be even more of a pain in the butt. But with the polynomial, it wouldn't be too bad. The polynomial here would give us 0.904833, etc. Whereas the calculator for e to the negative 0.1 would give us 0.904837. Like before, we don't see a difference in these things until we reach the fifth decimal place, the 100,000ths place. Excuse me. The sixth decimal place. We don't see a difference until we reach very far out there, which means that the polynomial is giving us an incredibly accurate approximation of what e to the negative 0.1 is. So let's go just a little bit further away and see if that accuracy drops. The polynomial here would give us 0.818666, etc., whereas e to the negative 0.2 would give us 0.8187, etc. And here we see the difference in the fourth decimal place. So that difference between the values is coming up sooner, meaning that the polynomial is less accurate than it had been a moment ago. If we go a full integer value, the polynomial is going to give us 0.333 repeating. E to the negative 0.1 is going to give us 0.367. We notice the difference, again, in the second decimal place, much sooner than we saw it in previous input values. So what we can see here is that they are exactly the same at the centering value, incredibly close when we're only 1/10 away. Still very close, but not quite as close when we are 2/10 away. And by the time we get to a full integer value away, the difference is starting to become noticeable. Still not tremendously large, but definitely becoming noticeable. Now, I would like to point out, we would start to notice the difference very quickly, especially on the left side, because e to the x, being an exponential function, e to the x is going to approach 0. It's never going to drop to infinity. It will rise up to infinity on the right side, but it will never drop towards negative infinity or rise up towards positive infinity on the left. Whereas a degree 3 polynomial with a positive lead coefficient is going to rise up, although it will never do so as quickly as an exponential does. But on the other side, it is going to eventually drop down. When we get up to some negative x values over here, we're going to see a massive difference very, 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 very quickly. On the right side, the difference will not be quite as apparent, but on the left side, it will be highly apparent because the value of e will remain positive and just approach 0, while the value of the Taylor polynomial will approach negative infinity, making for a very highly obvious difference. But as long as we stay relatively close by to our targeting value, they are very, very similar. Let's try a less obvious function. Something whose derivatives we might have to work a little bit harder at. Something that's maybe not centered at such a nice x value. This time, we're going to do a 4th degree Taylor polynomial, and we're going to do it for still a relatively simple function, but certainly less friendly of a series of derivatives. F of x equals the square root of x, and instead of centering at 0, we're going to center it at 4. So, we know that the 4th degree Taylor polynomial is the sum from 0 to 4 of the ith order derivative at 4 over I factorial times x minus 4 to the ith power. So as before, what we are going to need is the original function, which, for the purposes of differentiation, we'll find more helpful to write as x to the 1/2. Excuse me. We're going to need its derivative, which is 1/2 x to the negative 3/2. Excuse me, x to the negative 1/2. Then we're going to need the second derivative, which is going to be negative 1/4 x to the negative 3/2. We will need the third derivative, which will be positive 3/8 x to the negative 5/2. And then we need the fourth derivative, which will be negative 15 over 16 x to the negative 7/2. Now we might find it helpful to rewrite these using radicals because the next step is to evaluate them. Fortunately, we have a nice centering value in the sense that it is friendly to doing the square root. So, we need f of 4, which is the square root of 4, which is simply 2. We need f prime of 4, which is 1 over 2 times the square root of 4, or 1 over 2 times 2, that is 1/4. We need the second derivative, which is negative 1 over 4 times the square root of 4 cubed. The square root of 4, of course, is 2, so then we have 1 over 4 times 2 cubed, which ends up being 32. We need the third derivative, which is positive 3 over 8 times the square root of 4 to the 5th power. Two to the 5th is 32, times 8 is 256. So we have 3 over 256. And then we have the fourth derivative, which is negative 15 over 16 times the square root of 4 to the 7th, or negative 15 over 16 times 2 to the 7th. Sixteen times 2 to the 7th is 2048. These are our coefficients for our polynomial. Well, along with the I factorials. So, p to the 4th of x is going to be equal to 2. That's f of 4. Plus f prime of 4 over 1 factorial times x minus 4. Plus f double prime of 4 over 2 factorial times x minus 4 squared, plus f triple prime of 4 over 3 factorial times x minus 4 cubed, plus negative 15 over 2048 over 4 factorial times x minus 4 to the 4th. simplifying this is somewhat trivial. It's just a matter of some basic arithmetic. One factorial, of course, is equal to 1, so 1/4 over 1 is just 1/4. That part's easy. 2 factorial is, of course, 2. So negative 1 over 32 divided by 2 is going to be 1 over 64. And I will make this a subtraction rather than addition of a negative. Three over 256 divided by 3 factorial would end up being 1 over 512. The last one, well, even I'm going to need a calculator for that, is going to end up giving us negative 15 over 2048 divided by 4 factorial, which is 24. Now that would give us 15 over 49,152, but there actually is a common factor in there since the 15 is divisible by 3, and there is a factor of 3 in the factorial. So all told, when we simplify it, it's going to end up giving us minus or negative 5 over 16,384 times x minus 4 to the 4th. And that is our degree 4 Taylor polynomial for the square root of x centered at x equals 4. Believe it or not, again, without a calculator and in a time before there was electricity and cell phones and computers and lots of distractions, this is still preferable to attempting to do the square root of something. And again, it's not about just doing it at the centering value. If we actually did f prime of 4 and p sub 4 of 4, we would get the exact same value. It's about what would happen if we wanted to do 4.5 or 4.1 or 3.82, something very close to our centering value. Now, could we expand this? Could we expand all the powers of x minus 4 and then distribute the coefficients? Absolutely, we could. But I don't think that that would actually improve matters for us, and it would be a lot of extra algebra. I think it would be just as simple to leave it as it is, so that when we put in an x value, each one of those bases turns into the same thing. If we were to put in x equals 4.1, each one of them would turn into 4.1. Or to 0.1. If we were to put in x equals 4.02, each one of them would simplify to 0.02 and powers of 0.02. And I think that would make it much easier to work with than actually expanding it. Taylor and Maclaurin polynomials Maclaurin polynomials don't have much expansion to do.